Hello there, everyone. We are the two math magicians, and today we're just going to be discussing Hilbert's his infinite hotel paradox. Um, so yeah, we want to hear your thoughts about this too, but we're gonna give our own ideas and see what happens. So do
We're
you
not,
want to explain the problem?
we're not too sure why it's called paradox, as there's a solution to it, but it's a cool name anyway, so we'll just go with it. So there was this mathematician who thought, what if there was a hotel with an infinite number of rooms? So if we have this nice looking hotel, it's very big. It goes up all the way up and probably into space. But
Goes all the way up there. I'll just do a little infinity
yeah,
effect there.
and we're assuming that the hotel is fully booked, so every single room has a person in there. The problem says one person comes into the hotel, and what the solution is that in order to make space for that one person, everyone moves up to the next room. So if you're in room one, you go to room two, two to three. So it becomes the room changes room n plus one. As whatever number you are, you're going to one plus that. So it's just simple um, sequence. And how that works is that infinity plus one is infinity. So there is no, by moving everyone up by one, there should be no problem. So that's a good thing. But then the problem starts to get more difficult is when there's an infinite number of people coming in. And the mathematician said that, well, if an infinite number of people comes in, we can just assume that we can make infinite more space. And by doing that, everyone moves to the room double their number. So the person in room one goes to room two goes to room four, and etc. And obviously a room 500 going to 1000. So the bigger you get, the bigger the jump you have to make. And so obviously if you're in like room 5 million, you're going to room 10 million, which probably takes several years to make the move.
Yeah.
But the equation for this we have is n going to n, and that's what the problem
That
is.
gives you all the even numbers, and so then you're left with all the odd numbered rooms, and
Yeah,
they're
that's
all
true.
full.
Because if you double any number, it gives you an even number. So all the odd numbers become even. So all the odd numbers are left free. So that's why all the people they come in and they take the odd numbers. And by this theory, we're assuming that infinity plus infinity gives us two infinity. But then two infinity, we're assuming is the same as infinity. And this got me thinking. This got me thinking. What if we treated infinity like zero? So if you imagine you have zero and you add two zeros together, you get zero. Then if it's any other number, you'd assume zero plus zero is two zero, but two zero is the same as zero, as any number times zero is zero. So it's just an interesting thing because I like to see if zero as being the reverse of infinity. Infinity is the maximum you can get. Zero is the absolute smallest you can get. If you have a number two and you keep doubling it, you'll never get to infinity. And if you keep halving that two, you'll never get to zero. So I like to think of zero and infinity as opposites. Okay, that's me done talking. I'm gonna hand over to the other mathematician to talk about a cool theory that he has.
Yeah, so I mean, now suppose if you have like you have infinite people coming into the hotel, but they're on infinite buses. So you've got infinite buses, and each of these buses has infinite people. Then how do you accommodate for it? Because well, you've got more people, you've got plenty more people. And the idea was to use prime numbers because we remember that there are infinite prime numbers, and that's what I'm going to prove right now. And it's an interesting proof. It's proof by contradiction. So the first thing we're going to do is we're going to assume that there are finitely many finite primes. Assume that there's like a list. So the list would prime one, and then you've got prime two, and then you've got the third prime number, and then it goes on all the way to the nth prime number. So there's a finite list. So let's call like alpha. I like Greek letters, so I'm going to use alpha. Alpha we're going to call P1 times P2 times P3 times all the numbers in the middle times Pn. And then the key is we're going to be adding 1 to the end. And that's alpha. So let's just, to make this simpler, let's call alpha, we'll call it a plus 1. So you can see that a corresponds to the product of all of these prime numbers. Okay, so now there's two options if we have alpha, and alpha is an integer, right? So there's two options here. Either alpha's prime or it's not prime, okay? And if it's prime, so if alpha is prime, then we'll hang about, but alpha's bigger than Pn, right? Clearly it's bigger because it's the product of all of these numbers plus 1. It's going to be bigger than the largest prime. So we found a new prime number. We found a new prime number that's bigger than the supposed the biggest prime number. So alpha's bigger than Pn, right? So that's a contradiction because that doesn't make sense because we found a number that's bigger than the supposed biggest prime number. Okay, so that means alpha must be not prime. Okay, so the idea is that alpha is then not prime. Okay, well, what does this mean? Well, if a number's not prime, then it can be written as the product of a prime number, right? So if alpha's not prime, that suggests that alpha can be written as the product of a prime number. So I'm just going to say like some constant k times a prime number, which I'll just call pi. So pi is a prime number. So pi falls in this list of all the prime numbers. And k is just an integer, a positive integer like that. Okay, so if we put pi in terms of a, you can in terms of alpha. This means that pi divides alpha, right? Okay. So now let's do it for a as well. If we look at pi is in this long list of numbers, which means that a divides pi, right? Sorry, no, pi divides a because we can see it's in the big list of numbers. If you're multiplying a by a bunch of other numbers, that means pi divides a. Okay, so we have that pi divides alpha, but it also divides a. Now what we can do is we can kind of subtract them. If you know the basics of modular arithmetic, then you know we can just subtract them. So if I go up here, we can say that pi divides alpha minus a. So if pi divides alpha, which it does, because it's not prime, so it can be written as the product of a prime, and pi divides a because it's in the list of prime numbers, then it divides the difference between them. Okay, well, what does this mean? It means that pi times some number, let's just call it like t, is going to give you alpha minus a, and t is just another integer. Okay, well, what's alpha? Remember that alpha was just a minus 1, coming back to this. So we can write this as pi times t is going to be a plus 1 minus a. Okay, well, that's just 1. So we've shown that pi times t is 1, but t is an integer, and so is this prime number. So that doesn't make sense, because you can't have an integer, a non-zero integer, because it's a prime number, so it can't be 1 and it can't be 0. If you're multiplying two integers together that aren't 1, then you're not going to end up with 1. So that's a contradiction. That doesn't make any sense. So what that means is, that means that it's not prime. We know that this is wrong, so it has to be prime. Alpha has to be prime. But that can't be the case. That's wrong, because we found that's a contradiction. So that means our original assumption, there are finitely many primes, was incorrect. So that means there's infinite primes. And that's the proof that there's infinite primes. And what this means is if you have the hotel and you're shuffling people around because you've got infinite buses, each with infinite passengers, what you do is you take all the passengers in the hotel, all the passengers, all the people staying in the hotel, you take all of them and you move them from whatever room they're in to the first prime number, which is 2, raised to the power of that room. So they go from room n to 2n, 2 to the n, sorry. Okay? And then the people on the first bus, this is my bus. It's a terrible bus, but you get the picture. The people on this first bus, which remember is infinitely many people, people on the first bus go from seat number n to seat number 3 to the n. It's the second prime number to the power of that number. And then on the second bus, you take people, this is bus 1, this is bus 2, and then this is the hotel, clearly. You take all the people from their seat number n to the power of the third prime number, times, you take it from their seat number n to the third prime number to the power of that seat number. And then you keep going on, and we can keep doing that because we've got infinitely many prime numbers. And it will never overlap because the prime number to a power has the prime number as a factor. So it won't overlap with any of the others because they're all prime numbers. So yeah, that's what you do when you've got infinite buses with infinite people on them. Interesting.
Quite a lot of demand for the hotel.
Yeah, I know, they're getting a lot of money.
They're getting infinite of money.
It's true.
They can open up infinite more hotels.
They can. They have a lot of money.
Yeah.
It'd be a nightmare though. I mean, you'd be woken up in like the middle of the night. You'd have to go from room like whatever it is, n to like, and then a prime number like 17 to the end. You'd be going up. And then another bus would come, and it'd just be disaster.
And then you have to pack all this stuff and then move it, and then and then you probably got people's like you've got like an unmade bed when you arrive at the room, unless they have room service for the infinite rooms.
It's true. You were taking a long elevator ride.
And then when it comes to breakfast in the morning, you've got an infinitely long queue before you get your food.
Infinitely long queue. There's one restaurant, yeah.
And when you're leaving, there's an infinitely long queue just to leave, and there's not enough taxis to take everyone away.
It's sad, but there you go. It's an I'm not sure why it's called a paradox, because it
just sounds cool.
But I guess it does. But there you go.
Yeah, well, I hope you enjoyed that interesting maths problem. There's a lot of it on the internet if you want to learn more in-depth stuff about it. But this is just a basic, well, not really basic, but just telling you how it works and a cool prime number thing. And I hope you enjoyed. So
Thank you. See you later.
And remember, maths is the way.
Maths is the way.